think we can get started. So I'll introduce myself. My name is Kyle, and I am the vice president, the vice president of events at the Carleton AI Society. And I'm here with Koa and Victoria from our tech team. I'll let them introduce themselves. Koa.
Yeah, thanks, Kyle. So I'm Koa. I'm just a master's student here at Carleton University in the electrical and computer engineering. So today I'm just going to be introducing the concept of linear regression, and Victoria here is going to be showcasing some code to do exactly that. Victoria?
Yeah, my name is Victoria, as Koa and Kyle said. I'm also a master's student at Carleton in the computer engineering department as well. And yeah, I'll just be going over some code after Koa goes over some slides.
Yeah, so really quickly, next week at the same time, just a different place, Discord. These guys will be here, on Discord for an office hours. If you have questions about the event that are a little too complex to answer today, or you think of something throughout the week, you can ask them next week. And as well, we are sponsored by CPA Ontario. And lastly, you can find all of our socials. It's just usually Carleton AI Society, and all of that. So yeah, I will stop presenting and I will let Koa take over.
Thanks again, Kyle. Just going to have to share my screen here. All right, so can everyone see my screen?
Yep, it's good.
All right, awesome. Okay, so today in this workshop, I'm going to be explaining linear regression, which is one of the most fundamental supervised machine learning algorithms out there. So if you take any course in machine learning here at Carleton University or even online, linear regression is probably going to be the first algorithm you're going to be exposed to. Okay. So first, we're going to explain, what it is, what linear regression is exactly, talk about why it's important, and hopefully we can get a sense for, why it exists and what it's used for. And then once we're comfortable with the concept of linear regression in part 2, we can dive a little bit deeper into the algorithm. So I'm going to be talking about how the algorithm is actually implemented using some mathematical notation. But I'm going to try to emphasize the intuition more so than the technical details. So don't worry too much if the math doesn't make that much sense to you right now. And then finally, in the third part, we can talk about some issues that you should be aware of when using linear regression. And we can talk about some possible strategies to make linear regression work for you. Okay. So what is linear regression? Here's a couple of definitions I found online. So the 100-page machine learning textbook by Andrei Birkov, he explains linear regression as a popular regression learning algorithm that learns a model, which is a linear combination of features of the input example. And on towards data science, they call linear regression a tool for finding linear relationships between a target and one or more predictors. And finally, Jason Brownlee from the site Machine Learning Mastery, he calls linear regression a linear model. That is a model that assumes a linear relationship between the input variables x and a single output variable y. So all these definitions basically say the same thing. If you're given a feature set x and you have a target variable y, linear regression is basically a tool that allows you to model this relationship or describe this relationship. Okay, so here's some formal definitions of linear regression. So multivariate linear regression basically covers the general case. It allows you to estimate a continuous y target based on any number of features x. So the variable w here basically represents your model weights. So when you're making a prediction of y based on your features x, you can think of w as the parameters which tell your model which features are more important than others. And this is why we call them weights. So in other words, they apply a weighting to each feature x to control their influence on your prediction. And then beta 0 here is just a scalar, a constant biasing factor. So we're actually going to focus more on a special case of linear regression, where your x consists of only one feature. So in this case, your only weight is beta 1. And this is equivalent to finding a line of best fit. So if you look at the equation real close, it's really just y equals mx plus b, where beta 1 is your m, and beta 0 is your b. And this is just the equation of a line. So here's some examples to hopefully help you visualize both cases. So an example of multivariate linear regression could be when we want to predict the probability of university admission for a student given two features. In this case, their GRE general test scores and their CGPA, for example. So it's a bit hard to see in this 3D plot, but basically you have your probability of admission on this axis. and you have two features on the other axis, and you can expect that your probability of admission increases when you have a higher GPA and a higher GRE test score. And linear regression is a tool that will help you model or describe this relationship. And so on the other side here, we have the simple linear regression case where we remove the GRE score. So we're predicting based only on CGPA. And this is probably more familiar to you. It's just a simple problem of getting the line of best fit to the data available. Okay, so why do we use linear regression? Is it actually useful? So linear regression, although simple, is actually a very powerful predictive tool for many industries. So in business and marketing, you can imagine that linear regression is used to make forecasts or estimates. IBM actually makes the bold claim that linear regression has applications in even biology, that it can predict the future in behavioral and environmental studies, whatever that means. But in academics, linear regression is a very well-established and understood model that is also trained comparatively easy. So this makes it a very valuable baseline to compare other methods to. And just a teaser, linear regression can also be useful for our up-and-coming CAIS X KO competition, but there's no promises. But you should try linear regression on that problem. Okay. So now that we know exactly what linear regression is, we're going to talk about more about how to perform linear regression. And we can talk about its implementation. So we'll go through each element of linear regression using mathematical notation. But again, I just want to stress that what's really important here is the intuition behind it. So general understanding comes first. Actual understanding can come later. So now, a good linear regression model is one that predicts values that are as close as possible to their true values. So nobody wants a model that doesn't give you predictions that you can rely on. And basically what this entails is that you want to find the exact weights to your linear model. In this case, it's W and beta that we showed earlier, which minimize an objective function that defines a cost or error for making wrong predictions. So if you assign a penalty for being a bad model, your model is going to try to learn the weights that make it a good model, which minimizes your cost. And this basically implies that your model will only be as good depending on what cost function you define. So if you don't understand this right now, I'll hopefully visualize this soon, so don't worry. So a common mean squared error, or MSE loss, this is commonly used in linear regression models. And this basically measures cost as an average of the squared distances between your predictions and their actual label. So if you look at the equation here, this is just your prediction. This is the actual label. We take the squared distance and average it. And that is what we define as a cost for a linear regression model. So we can go back to our probability of university admission example, the simple case, with only one feature, in this case CGPA. And so in this first example here, you can see that our linear model doesn't actually predict very well. So it's predicting that people with low CGPAs are very likely to get accepted into university. And conversely, people with very high GPA are not going to be accepted. So this is obviously wrong. And this is an indication that our model weights are probably not correct. So we can actually visualize the cost, the MSE loss, associated with this model weights here on the right. So this curve right here basically represents the cost function we said earlier. And obviously the cost differs based on your weights. And in this configuration, we can say that the cost is very high based on this dot here. So in the second example, we try a different set of model weights on the right here. So we actually find a very good fit. And the model, we can tell this because the distance between the predictive line here and the actual training samples is minimal. And this is very reflected in our cost function graph here, where it's actually the lowest. So hopefully it's evident now that getting a good linear regression model is simply the process of finding the weights that minimize this cost function. So we have to talk about exactly how we're going to do that. So it's actually not feasible to try out every possible weight, record the cost, and repeat for eternity. There's infinite amount of configurations you can have for your linear model, and just finding the best one is not that simple. Well, with the MSE loss we defined earlier, there are actually two approaches to finding the best possible solution. The MSE cost function can actually be solved analytically using the ordinary least squares method. I won't go into the exact details here, but you can think about it as applying this formula to your data points, and it will spit out the exact best weights every time. So when you can use analytical solutions, that's great. But in most cases, it's not possible to apply analytical solutions because they usually require a lot of computational resources and time. And this is especially true for when you have very large data sets. So in most cases, analytical solutions are just not possible. So the best we can do in this case are numerical solutions, where we can get an as good or a good enough solution using numerical methods. So this basically involves making an initial guess at your weights, thinking about how to improve your solution, and then trying again. And this is basically an iterative process where you hopefully can converge or zone in towards a rough estimate of your answer pretty quickly. So one of the most popular numerical methods for optimization is gradient descent. So that's what we're going to talk about next. And so, like I said, we have to start somewhere. So in gradient descent, we make an initial guess at the model weights. So if we go back to our university admission problem, we can pretend that we start with the bad model I showed you before with this cost over here. So in the second step, we compute the cost of the model using those weights, and we get this cost here, which is pretty high. So we obviously want to reduce that. And then since the MSC loss function we defined earlier was differentiable, we can compute the derivative or the slope of this cost function at any point. So we're going to do that here, and this is represented by this arrow over here. And what this arrow tells us, this arrow basically tells us the direction that we want to go to reduce our costs, which is very important for us. So we actually use this information in step 4 to update our weights with a learning rate alpha. So the learning rate controls basically how much we want to update our weights based on this gradient or slope. And basically, we just repeat this process from step 2 to step 4 until we eventually converge into a solution that satisfies our problem. So the learning rate actually has to be chosen very carefully. When your learning rate is too small, your updates will actually be negligible. So you can imagine if your alpha is basically 0, your cost will never update, or your model weights will never update. So basically, your cost stays the same no matter how many iterations you go through. And conversely, if your learning rate alpha is too high, you can imagine that you take too big of a step in this direction, and you basically bounce around your optimal solution. You just go back and forth, and you never reach a good enough solution. So you have to be careful when choosing learning rate alpha. Okay, so with that in mind, we're gonna have to discuss how you choose a linear regression model. And I have a couple of questions here. So which linear regression model best describes my data is in this figure, which I stole from Amazon. And then you kind of realize that some of these aren't straight lines, which kind of conflicts with what I told you earlier. So yeah, so some of these models don't even predict straight lines, which you kind of question whether these are even linear regression models. And the answer is, these models actually could be linear regression. So as Kevin Murphy so eloquently explains in his book, Machine Learning, a Probabilistic Perspective, a linear regression model is called a linear regression model as long as it's linear in its weights rather than its features x, which is a little bit confusing. So I'll explain a bit better here. So linear regression models can actually model nonlinear relationships using what is called a basis function expansion. So basically, instead of applying your weights to the features directly, like in here, like we had before, you apply them instead to a nonlinear transformation of your features, which is represented by phi x here. But it is still linear because it's the weights that are linear rather than the features. So this case example right here, you can obviously tell that it's linear. And this one, although you would assume it's not linear because of these power terms, in linear regression, we would call this model linear just because of the weights. All right, so now we can just revisit this image again. Knowing that the linear regression can model more than a straight line through data, we can now ask, well, what line should we model? And well, we want one that is complex enough to model the training data well, but is simple enough to generalize to unseen data. And this is what we call the bias variance trade-off problem. Okay, so an underfitting model is one that performs poorly on training data because it's too simple. So we say that the model has high bias. It just kind of assumes some model. It doesn't really change even if you give it different training data. So you can imagine for this case here, we could just kind of assume a straight line. And no matter what the data was, we'd always assume a straight line. So we call this high bias. It doesn't really care what training data you give it. And then conversely, an overfitting model is one that performs a little bit too well on the training data and becomes so complex that it does terribly on unseen data. So we say that the model has high variance, right? So in this case here, we have an overfit model because it tries to, it goes too far. It breaks its back it goes through every hoop to try to predict each training sample perfectly. And basically what this means is that if you change the training samples, even if it follows the same trend, your model will change drastically, or it will vary drastically with changes to your training samples. So we want a good model that achieves some sort of balance between these two extremes, which is the bias variance trade-off problem. Usually in practice, overfitting is the bigger issue of the two. When you kind of look at your data, you can kind of assume a general trend and limit the bias problem. But it can be difficult to limit the complexity of your model while also seeing good results when you train. So when you're overfitting, It could be a sign that you're using too many features, or in the case of an n-degree polynomial relationship, maybe your highest power is just simply too high. So you can imagine using 3 features is simpler than using 100, and using a 2-degree polynomial is simpler than using a 10-degree polynomial, for example. And then we can sort of restrain the model to be simpler by introducing regularization. We're going to talk about L2 regularization here. So what is L2 regularization? Well, it's basically a strategy that adds a new term to your cost function. In this case, it adds the squared magnitude of your weights based on a hyperparameter C. And you can think of this as encouraging the model to drive its weights towards 0, telling it to somewhat ignore some features when making predictions and making the overall model simpler. So that's this term here. And then this C parameter basically controls how much you want to penalize based on your weights. So if C is 0, this term basically disappears and your model is no longer regularized, and you're likely going to overfit. And then conversely, if C is too high, then you introduce high bias and your model no longer cares about the actual training data. So it is a hyperparameter because C is something that you as a user chooses. Okay. And once you find your balance, L2 regularization will definitely help you improve your models. Okay, so I hope you see now that linear regression is a powerful tool for many situations, but it is nothing without the data to back it up. So like many other supervised machine learning algorithms, you're going to need to train on a lot of data for linear regression to learn an appropriate model. And the more complex the relationship you want to model, the more data you're going to need. So when you go and work on your own problems, you should think twice about whether you have enough data to make linear regression feasible. So that about wraps it up for this theory part of this workshop on linear regression. I hope everything made sense. Then we're holding office hours next week at the same time. If you have any questions on what we talked about today. Before I hand it off to Victoria to show you linear regression in Python, I'd just like to highlight an upcoming opportunity where you can apply what you learned today to an interesting problem. So our club CAIS is hosting a free-to-enter machine learning competition for undergraduates in the 2022 winter semester. I think there's about, I think it's $150 in rewards, which is pretty cool. So you should check out CAISX if you're interested. All right, thank you. Victoria?
All right. Just gonna wait for you to stop sharing your screen.
Yeah.
You guys can see my screen?
Yep.
Cool. So yeah, as Kwa said, just going to be going over a little notebook discussing some of the things that Kwa talked about in the PowerPoint. So in this hands-on portion of the workshop, we'll be using the linear regression model from scikit-learn, the ordinary least square model from stats models to perform linear regression. So this notebook uses code, data, information from these sources just to make sure that I'm telling the truth here. And over this notebook, we'll be importing a data set, checking out the data set and doing some exploratory analysis, training the model or training the linear regression model 2 different ways, and then exploring different versions of gradient descent. So first, just going to import some libraries here, and then we're going to import the data set. So Kwa kind of alluded to the data set in his PowerPoint. We're going to be looking at a data set that tries to predict or shows the chance of admission based on some criteria that the students have. So the data set, if I just show it down here, the data set has 9 columns, 7 of which will be useful for features, and then finally the chance of admit column right over here. So in predictive models, there's response variable, also called the dependent variable or the target variable, which is the variable that we're interested in predicting. So we're going to try and predict the chance of admit column. The independent variables, also called predictors or features, are 1 or more numeric variables we can use to predict the response variable. So given that we're using a linear regression model, we're assuming that the relationship between the independent and the dependent variables follow a straight line or linear. So before we start the modeling exercise, it's good to take a look and see what our data looks like. So first we can use this describe method to look at some statistical attributes of our data and check out how many non-null data points that we have for each feature. So here we can see, you know, the mean, the standard deviation, interquartile ranges and such for the features and our the variable we're trying to predict. We can also see the number of data points we have for each of the columns, and that's important to tell us whether or not we're missing some values. If we were missing some values, we will have to look at whether we want to drop those rows or do data imputation, and that's something we'll discuss in a later workshop. But for now in this one, we have the exact same number of data points for each feature, meaning that we're not missing any values. We can also use this shape attribute to look at the shape of our data. So 500 meaning we have 500 rows and 9 columns. We can also use the info method with the parameter verbose to look at the amount of rows we have for each of the columns and the data type. So here, GRE score is an integer, but CGPA is a float. So it's also good to take a visual look at what we're trying to predict. A good way to visualize how our data behaves is to look at pair plots. So with these plots, we can see how each feature relates to one another. So we're going to look at these pair plots. This one is going to take a little bit to run because pair plots are a little bit intensive. So what essentially these pair plots are is we're going to have all of the columns on the left and on the bottom, and we're going to plot scatter plots of each feature against one another and against the chance of emit, the variable we're trying to predict. There we go. So as you can see, we have a whole bunch of scatter plots. We have the columns on the left, and then them also on the bottom. So if we take, I don't know, one of these plots for instance, we can look at serial number versus chance of emit. Serial number is not a column that'll be useful for a feature because it's just a set of numbers. But if we look at GRE score versus chance of emit, we can see that it's linear in its relationship. So generally, as someone has a higher GRE score, they have a higher chance of getting into the school. Same with the TOEFL score, also with CGPA. There's kind of a trend for these three right here, but not as obviously linear as this one here. Another way to look at the data is to plot histograms of the distribution of the features. So then we can look at how the different features are distributed across their ranges. So, you know, GRE score goes from 280 to 350. So P is discrete, kind of. CGPA has a normal-ish shape. So the important part here that to look at is to see if we have any outliers. Currently in this data set, there are no outliers, but if there were outliers, we would have to figure out what we wanted to do to either get rid of them or investigate them. So as seen in the pair plots, we can see that GRE score, the TOEFL score, and CGPA have a decent linear relationship with the chance of admit score. So we can take a further look at those plots. So as we can see, these are generally linear. Here again with chance of admit versus TOEFL, linear. And then finally, the CGPA versus chance of admit, linear as well. So these might be really good features for us to use to predict chance of admit since we are doing linear regression. So some features will be more useful than other features in training a classifier. And some features can be redundant. So a good way to determine this is to look at the correlation between features and the target variable and between the features themselves. So if we plot the correlation here, Similar to the pair plot, we have all the columns on the left and all the columns on the bottom. We can see this correlation value here. So we can see that GRE score has a 0.81 correlation with chance of admit, meaning that it's probably pretty good or pretty useful to help predict chance of admit. CGPA has 0.88, which is also pretty high. TOEFL score has 0.79, also pretty high. But if we look at the relationships between each other, we can see that, for example, CGPA and the TOEFL score have a correlation of 0.81, meaning that they themselves are correlated to one another. So if we were in a case where we wanted to reduce how many features we were looking at, we might decide to only keep one of the two because they're very correlated to one another and correlated to chance of admit. Do we really need both? So as described in the slides, there are two different ways to train a linear regression model. We can use ordinary least squares or gradient descent. So we're actually going to try both. But it's really important when training and testing a model that we split the data into train and test. Sometimes we can even split the data into train, validation, and test, where we train our model on the training set, apply to the validation set, and cycle between the two to tune our parameter choices, and then finally test on the test set to have an accurate estimation of the performance of our model. But today, we're only going to be using train and test since we aren't performing hyperparameter tuning. So we are going to read in our data set, perform our split. Next, we're going to train our models. But to test a model, we need a metric to define the performance. So today we're going to use the metric mean absolute error, and it's defined by this equation before. It just averages the error over all of the data points. So this will allow us to average the amount of error between the model's predictions and the true value over all of the data points. So we're also going to report the time that it took to fit our models, just so we can also look at that. So first, we're going to do ordinary least squares explicitly. So we're going to use the NumPy package to perform some matrix operations to solve this equation that Kwa showed in the slides. So that line here is what's doing the matrix operations. And by doing that, we get the bias and the weights here. Our final mean absolute error is about 0.04, which is actually pretty low. And it took us about 1.5 milliseconds to do that. Another way to apply ordinary least squares is to use scikit-learn's linear regression model. So this model is essentially doing the same thing under the hood. So as we can see, we get these same values for our bias and our weights, the same error. However, this one took a little bit longer. Now, if we had a larger data set, the scikit-learn model will probably be faster because under the hood, they take some shortcuts and stuff using code and math to make their code run faster than, let's say, me running this matrix operation line. But for this data set, since it's so small, our explicit method was faster. There is also a stats model, ordinary least squares, that we can apply. It does the same thing. We have very similar coefficients and biases. But the nice thing about the stats model is that when we can print the summary, we get this importance value kind of here. So this is kind of similar to stats, where we perform a test to see something is statistically significant. And let's say we have like an alpha of 0.05. We want our p-value to be less than alpha to say that it's statistically significant. So these values kind of do the same thing. The lower it is, the more significant the feature is for our prediction. So here we can see that a GRE is significant because it has a very low p-value, kind of like how we thought so before, same with CGPA. However, these two features are not as useful. They have a higher p-value. So from our many forms of doing linear regression, we can get this equation that will predict for us the chance of admit given any student that has these features. So from our OLS summary here, we can determine that these two features are probably not useful for our model. So we can drop them and let's try again. So when we drop them, we get these biases and these weights. We get an absolute error of 0.43, which is slightly higher, like 0.001 than what we had before, but it's like almost a negligible difference, and we have less weights, thus having a smaller model. So we can define our equation again, and yeah. So if we plot the performance of our four methods, we can get the mean absolute error for all the cases and the time it took. So our best performing model was the explicit and the sklearn. The fastest one was our explicit use of the numpy package. Yeah, but our feature selected one does perform relatively close to the other methods. So the three methods that we used before are all performing ordinary least squares, but we can also use gradient descent to solve our problem. But there are actually many different forms of gradient descent that do slightly different things. They all essentially perform gradient descent similar to how Qua explained, but they do take some mathematical principles to add, some shortcuts. They apply some extra things to make it faster or just better in general. So there are a whole bunch of methods that you can look up online, different versions of gradient descent that are better for different things. So here I'm just going to take 5, use them. Let's see what error we get. Let's see how fast they run for our case. So there are no linear regression methods that I can give a gradient descent optimizer to. So what I did here is I made a very shallow neural network of 1 layer and 1 unit, and that essentially performs linear regression. We'll cover neural networks in a later workshop, but essentially it's just doing linear regression. So first, we're going to create a 1 layer, 1 unit neural network, and that's this line right here. We're then going to compile the network with an optimization algorithm. That's these lines here. We're going to fit the model and train over 25 epochs. And then we're going to apply the trained model to the test data and store the mean absolute error. So again, this is just going to happen for all of these optimizers. And then we can just have our results here. So for these 5 optimizers that we used, we have the lowest mean absolute error, I believe, is the Adamax. And the fastest one is stochastic gradient descent. But this can change. This is different from the results I had earlier today, and this is different from the results I had earlier this week, just because the training set data, the train test split was different each time, and each of these methods started a random point to begin with. So depending on how well that point was to begin with, it'll take a number of iterations to get to the minimum. But that's all we had for the code for today. So make sure to check us out on Facebook, Instagram, and our website.